Okay, we're going to talk about next the extent of reaction. And the extent is a concept that's very useful for calculating outlets of reactions, outlets of reactors, and so forth, and determining various quantities. So we've gone through in class, and we've had previous videos where we've calculated how much of a particular species is converted. An extent is kind of a way to do that. So let's look at this. Let's start with an example here. So in this case, we have this reactor with this inlet here of 100 moles of SO2, 75 moles of O2, and the outlet is 25 moles of O2, and some unknown amount of SO2 and some unknown amount of SO3. And really what we want to do is find out what these are. And the reaction that's taking place in this reactor is shown right here. Just 2SO2 plus O2 goes to 2SO3, a reaction we've used many, many times. Now, we have this set up right here, and you will recall that we've done similar stuff in class where we've set up equations. So we can write for the reactants, N out plus N reacted equals N in. And so this applies to the reactants, and so if we wanted to, we could go ahead and plug in the numbers for O2 since that's what we know. And so the out is 25 moles of O2, in is 75 moles. So if we just plug that in there, we would find out that N reacted is equal to 50 moles. And if we use this value, we can use the stoichiometric ratio to find out how much SO2 reacts away, and we could also find out how much SO3 is produced, again using the stoichiometric ratio and this number. Now there's an alternative way to go ahead about trying to solve this problem, and that's using extent. An extent equation is very similar to this one right here, except the extent equation is written as this. N out is equal to N in plus nu I times this funny little symbol here, and this funny little symbol is the symbol for extent. It's actually a Greek letter, psi, the Greek letter psi, and it represents the extent. So oftentimes, however, I'll just call this the extent rather than calling it by its Greek letter, but it's the Greek letter psi for, and it represents extent. This equation right here is the extent equation. And it's so important. I'm going to put a little box around it. And it more or less, the extent tells us about how much a reaction has proceeded forth. So how much of that reaction has occurred. And that's what the extent does. That's the value here that tells us how much of that reaction has occurred. The other part here is this Greek letter here, nu, lowercase nu, and it represents how much, how do you take into account individual species, and it's more or less it's the stoichiometric coefficient in a reaction, except with one stipulation. It's negative for reactants, positive for products. So that being the case, we can write out what the stoichiometric coefficients in the extent equation are for all the species. For O2, it's -1 because remember, it's a reactant. And then SO2 is -2. And then SO3 is +2. And there we have it, the three stoichiometric coefficients that we would use in our extent equation. And this kind of illustrates why oftentimes when we're doing our reactions, when we're balancing them, it's often useful to use whole numbers when writing out this reaction, these reaction equations, but we don't have to. We can go ahead and use fractions, and in the end that will just scale what the extent is, but oftentimes it's easier just to work with whole numbers when we're doing this. So anyways, let's go ahead and look at this. So in this case, we can go ahead and calculate what the extent is based off of this information. So let's go ahead and do that. So what I'm going to do next is just find out what the extent, and then use the extent to find out how much is leaving this reactor for all the different species. So NO2 out equals NO2 in plus the stoichiometric times the extent, which is minus times the extent, minus the extent. In this case, again, I have -1 as the stoichiometric coefficient. So I can go ahead and take the information I have, it's 25 moles out and 75 moles in, and I can go ahead and solve for extent. And if I do that, I'm going to have that the extent is 50 moles. Now, one thing again I just want to point out is that the extent has units of moles. Notice that it has units of moles, and it's not specific to a particular species. It's not 50 moles of O2 or 50 moles of SO3 or anything like that. It's just 50 moles in this case. And that's our answer for the extent. And now the good thing is I can go ahead and find out how much is leaving our system. And SO2 out is equal to, let's see, we have 100 moles coming in, and then it's -2 times 50 moles, and so NSO2 out is equal to 0 moles. And then we can do a similar calculation for the number of SO3 out, but in this case we would have instead of -2, +2, and then starting with 0. So number of SO3 out is 0 plus 2 times 50, or in other words, SO3 is 100 moles. So, and there we have it. Now we have, using our extent, we were able to find out how much of the species were coming out of their system. So let me just go ahead and recap that the number of moles exiting the reactor is number of moles in plus the stoichiometric coefficient times the extent. So let me just put a box on that. Or alternatively, sometimes we may not know the extent and we need to solve for it, so we can just go ahead and rearrange this equation, and we'll go ahead and get this for our extent equation, and that's just this equation in box rearranged. And that's the extent, and it's useful again when we have many different reactants and many different products. We only have to calculate oftentimes one unknown, and then once we know that one unknown, we can go ahead and calculate what's leaving a reactor once we just know that extent. So it's a very useful quantity for analyzing and studying reactors and reactions, and that's extent.